Thank you for joining me today. Here's the agenda of our presentation. We will be covering the purpose of the project, assumptions that I have made, the data engineering and cleaning that needed to be performed, how I developed the recommender, and the results of the analysis and verification. I will cover the next steps and some lessons learned. The purpose of this project was to build an objective recommender that will assist a FIRST Robotics competition team in selecting alliance partners for the final rounds. The output of the recommender will be a list of possible pairings that the team could employ. I believe that if we analyze past match scores, an objective recommender can be developed. There are two parts to the data. The first part is the qualifying rounds. This is the data that will be used to develop the recommender, and is the data available to teams for making decisions during the regional competitions. The final round data can be used to somewhat verify the recommender. Matches are played by two alliances of 3 teams each. Alliance scorer points, and winners are determined by the alliance that has the most points. Qualifying round alliances are randomly formed. Teams will play several matches to determine the ranking for the teams. After the completion of qualifying, the top 8 teams get to choose their alliance partners. This is when the tool comes in. The tool will provide objective information that the team can use to choose alliance partners. I assume that better teams will aggregate higher scores over the course of qualifying rounds, even though the scores are generated by alliances. Using a large number of matches for model development, a more accurate probability of win will be calculated. I assume that there will be additional criteria used in the final selection of an alliance partner. My data was downloaded from the website thebluealliance.com. This site collects information on all the FRC competitions worldwide. The information is stored and disseminated via their app and other methods for teams and spectators to consume. Data is reported by match and alliance. For my project, I will have to transform that data into a team focus. I used data for the years 2016 through 2019. For event matches, I downloaded approximately 72,000 rows. This was turned into around 434,000 rows after transformation. The awards files contained about 16,000 rows of data. For the event data, the data was formatted as you can see from the Blue Alliance figure. What I needed is the data to look like in the figure below. So for each row that was read in, 6 rows of data needed to be created and a win flag needed to be set to identify the winners of each match. I also had to parse the year region match column into separate year, regions, rounds, and match columns. For clarity, I gave each round a more descriptive identifier. For a first look at the data, I plotted the scores from each year, color-coding them by win, yellow, or loss, green. This plot shows the effects of the new game being played each year. The method of scoring changes each year, and the range of possible values is different. To be able to compare this data, the scores would need to be standardized. I also looked at the means and the standard deviation for the scores, and I calculated these for each year, and I separated them into rounds that was being played. This is important to understand since as the matches go from qualifying to finals, the mean scores increase for each round. This helps set expectations as the teams go into final rounds and will be selecting alliance partners. Now that each year and round have been standardized to a 0 mean and a unit standard deviation, the data for each year is now comparable, and we can now treat it as one data set. Here's the data distributions by round for all the standardized data. I have outlined the mean value with a red box for easier identification. For all of the charts, the data has a normal distribution. Because of this, We can use analysis techniques that assume a normal or Gaussian distribution and not have to account for it. I also noticed a darker green region. This is the overlap of the wins and loss data. This is an indication of scores that could either win or lose a match. As the scores move from qualifying through the final rounds, you'll notice there's a change in shape. The overlap in qualifying is broad and tall, indicating that there are more possible ambiguous scores. In the final round, the overlap is narrower, and it is also skewed to the right. Even though the scores are higher, it still does not guarantee a win. A common discussion within teams. Are the awards important? When looking at the figure on the left, I have graphed the number of matches won versus the number of awards won. You can see that teams that have won more matches are also teams that have won more awards. Remember, this is only for the 4-year period of data being analyzed. This may not be a feature for selecting your team to join your alliance. I do think it's an indicator of teams that have well-established processes and are consistent performers. I did include the table that has a random sample of records to further demonstrate the results. There is one more step of preparation needed. The categorical data, regional names, and the round columns need to be turned into a numeric value for processing. For the development of the model, I used year, standardized score, regional number code, and the round number code as features for the model. A logistical regression was used to determine the probability of win and the probability of loss. This also set the weights and biases of the model so that new data can be run through the model and calculated the probability of win and losses for that data too. The new data does not change the weight and biases of the model. To create the logic for the recommender, I extracted the data from the 2019 Oklahoma City Regional. I extracted only the qualifying rounds to emulate the data the team would have available for decision making. My first step was to configure the data into the correct format. I then ran it through the model to assign a probability of win score to each match. This figure is a comparison of the probability to win and the match non-standardized scores. You can visually determine what the score would be for a selected probability to win value. For instance, if you are seeking a 60% or better probability of winning, you will need a score of 50 or greater. Here's a plot of the mean score and standard deviation for each team. The mean score is the average score each team achieved in match play. The error bars show the range of scores for each team. In my assumptions, I said better teams will aggregate a higher score. Because the scores are actually the results of 3 teams working together, it is important to look at this chart. The error bars are an indicator of how other teams affected the team's score. If the error bars are large, this indicates that the team was not necessarily the strongest team on the alliance, and other teams actually had more of an effect on the overall performance of the alliance. The recommendation is built in 2 steps. The first step, the subject team is paired with every other team and the mean and probability to win is calculated. The second step is a little more complicated. The pairing is compared to other teams in the event. If the team would increase or at least keep the mean score the same, the team is added to the alliance. This is done for all the teams, and a list of selections is generated. Here's a sample of what the generated list would look like. You see 3 teams that are suggested for an alliance, the mean score, and the probability to win for those teams. Combine this with the scouting information that was collected and the final choices can be made. Factors to be considered. The mean qualifying score is used to make the recommendation. Scores in final rounds are always higher. There's another criteria that makes a good alliance partners. How well did the team play the game? Do they have a capability that is better than yours? Was their robot reliable? how accurate was their robot with the game elements, and our history with that team. There is not a great way to determine if the recommender is right. So I retrieved the actual alliances from the event. I used the recommender to make the same recommendations. The score column has the scores the alliance achieved in the quarterfinal rounds, and the record column contains whether the alliance won or lost the matches. A win equals 1. Teams with higher probabilities of win fared better than teams with lower probabilities of win scores. From the mean score chart, there is a 23% lift in the scores from the qualifying rounds to the quarterfinal round. If we look at the standard deviation for each round, they are all consistent for the first 3 rounds. So if we choose a team with scores that are higher, we can also be more confident in the recommendation when it is paired with the probability of win. To help verify and give another data point to the decision maker, I used a clustering algorithm to see how the alliance data grouped together. I used a mean shift version of a k-means clustering. I chose this because I did not need the number of clusters to be identified before I ran the algorithm. That was determined during processing. The figure on the left is a clustering of the alliances recommended. The color groups identify alliances with similar characteristics. If there was a conflict in getting a team for a recommended alliance pairing, because the preferred team had been selected, the color group could be used to select a substitute team. I also ran the mean shift against the team scores. The results of this did not provide any meaningful information. I have only shown this for completeness and full disclosure. So there are some things that could still be done. The code in the notebook should be converted to a series of Python definitions in a class so it can be run from the command prompt or used in another program. There should be some rework of the data cleaning processing to speed it up. That process took hours to complete. A series of lessons should be developed from the workbook to teach the tool and the processes to student members of the team. A JSON file reader should be developed so that live stream data can be captured at regional competitions. A predictive model could be developed from the data that will predict the team's performance over time. A pre-event scouting tool could be generated to report on the teams scheduled for future events. This tool could report on each team's past performance, awards won, and predict each team's performance. Here are some significant lessons learned from the project. First, after you complete time-intensive processes, save off the record. If you have to restart the program, you can start with the process data and not have to start over with processing of the data. Data preparation is important, and having a plan for how the data is going to be used. This way, you don't have to recreate an artifact after it has already been deleted. This last one seems like common sense for a programmer, but it still was a problem for me. Be aware of the command and reserved words. This could cause the program to misinterpret the desired action and cause an execution error. Thank you for your time.